We're going to talk a little bit about pendulums today. Everyone should be familiar with what a pendulum is, what they look like, but just as a refresher, uh, first, a pendulum, it swings back and forth due to tension and gravity. You can see here on this diagram we have a red sphere or circle, and it's hanging from a string. There's tension in that string due to the force of gravity pulling down on that object, on that mass there. And as it swings, it moves to the side. You can see we have that gravitational force broken down into x and y components, or sine and cosine, to get our components of it. We won't do a whole lot with the sine and cosine in this particular unit, but we've done that before, and you guys should be familiar with that concept, like what we saw with inclined planes. Another thing with the pendulum is it cannot reach a higher point than it started with due to the conservation of energy. If there's no outside force acting on it, it's not going to get higher than it started from. So even though it's swinging, it may pick up some velocity. It accelerates as it moves downward. Then as it comes back up, it slows down, and eventually it stops before it reaches its maximum height of where it started. If there's no friction, it would end up at the exact same height it started. In most realistic situations, we do have some friction and outside forces reducing that velocity and speed down. On the next slide, we'll look at some graphs. We can see that the motion is going to be a sinusoid or wave type motion. If we're starting from the top spot, if you're creating a graph on it, it's going to look more like a cosine graph, but in a pendulum, it is a wave type motion. Hopefully you saw in our lab activity that the period is not affected by the mass of the object. Doesn't matter what that mass is. We could do some deriving of the equation to get this equation down below. Instead, we'll just give it to you from the formula sheet. That way you don't have to do any diffie-q or anything like that. But time of period is affected by both the length of string and gravity. Typically we're on Earth, so gravity, most of the time we know gravity is 9.8. In some cases you may have to solve for gravity if we're pretending we're in a different situation, like on the moon. So as we can see on this equation, the time of the period is big T equals 2 pi times the square root L is the length of our pendulum string, divided by the acceleration due to gravity, or g in this case. So that's the equation we'll look at using. We'll do some practice problems with that here in just a minute, but first we'll take a look at a couple graphs. So our first graph or diagram is going to be looking at the energy of a pendulum. So first question is, was potential energy the greatest? So I'll give you a moment to think and decide which spot 1, 2, 3, 4, 5 you think is the greatest. So we're talking about potential energy here. Hopefully you selected either points 1 or 5, or hopefully both of them. Points 1 and 5 are the greatest height, so if we look at our potential energy equation, P equals mgh, m and g are not going to change. The only thing changing is the height, and those are our highest points. Was kinetic energy the greatest? I'll give you a moment to think on that one. Hopefully you're thinking of conservation of energy, and you end up selecting point 3. Point 3 is our lowest point, so that potential energy has been translated into kinetic energy. Finally, how does the energy of the pendulum change as it swings? So we want to know what's going on. We know potential energy is greatest here, kinetic is greatest here, potential is greatest here. So if we go through one loop, you can make a graph showing how that energy changes. Essentially what we want to know is the energy overall remains the same, but the kinetic energy increases closer to the bottom, while the potential energy decreases. So we got high potential, it decreases, and then the potential increases. Kinetic does the exact opposite of that. So you can make a graph showing those changes in potential and kinetic energy. Some more graphs dealing with pendulum. Now we're looking at the motion. We'll deal more with simple harmonic motion in our next week. but right now we're looking at just how that graph looks like. So if we have these points here, A, B, C, D, E, F, and G, it labels them on the graph. You can see the position. It starts at a high, and then it drops down, and then it comes back up, and we have this change in position over time. Velocity is very similar, except for now we become negative, or zeros in the middle, and it becomes negative. So that's what we're looking at on these pendulum graphs. The first one doesn't look to be labeled correctly. Our low spot should be D, so that one could use some correcting. I pulled this off the internet, so that one could use some correction on that. Next, we'll look at some example problems. Our first problem we'll look at is a 3.5 meter long rope hanging from a tree. Acts like a pendulum when a 35 kilogram child holds onto it after running. So essentially we have like a rope swing here and a child swings, and we want to know how many swings they complete in 6 seconds. So they have 6 seconds on the swing. We want to know how many swings back and forth they complete in that time. So in this case, we're looking at, we have a length, we have a mass, and we have a t, or a period, or a total time, not a period time, but a total time. So first, we probably want to use the equation for the period that equals 2 pi, the length of the string over gravity. In these cases, we're going to assume we're on Earth. Unless we say otherwise, we're going to assume we're on Earth and gravity is 9.8. Remember from your lab, the 35 kilograms we don't have to worry about. The child's mass is not going to affect the time of the swing. So first we plug in what we know. We have the length of 3.5, gravity of 9.8. All you have to do is type in your calculator, then 3.5 divided by 9.8, take the square root, times 2 pi, and we should end up with a time of 3.75 seconds. However, the question is not answered yet because we want to know how many swings the child completes in 6 seconds. So they complete one full swing going back and forth one time in 3.75 seconds. So then we have to figure out how many they do in 6 full seconds. So to do that, first we're going to take our 6 seconds and then we'll divide it by the time for one swing, which is 3.75 seconds, and that's going to give us total number of swings. So you type that in your calculator, 6 divided by 3.75, and we end up with 1.6 swings for this case. So that 3.5 meter long pendulum gives us 1.6 swings in 6 seconds. Again, the mass is not affected, so we don't have to worry about the mass in that case. We'll do one more example problem together. In the second problem, we have a clock, a large clock, kind of like Big Ben. It's being constructed, and developers wanted to have a pendulum that swings a 125 kilogram object across every 3 seconds. So it means it wants to go across one time every 3 seconds. So we want to know how long that pendulum has to be in order for that to take place. So first, we have to figure out how long the period is. So if one swings 3 seconds, we want one full time. We want one full swing, one full wave. So we need to go back and forth. So we have to take 3 and multiply it by 2 to get that total time, because that's half a period, what we know right now. So that means it's going to be 6 seconds for one period. So 6 full seconds for one period. In this case, it would be 10 swings in a minute is what they were aiming for. So then we go on and plug that into our equation. We have 6 is our time for a period. 2 pi is still in that equation. L is what we don't know, and again, we're still on Earth, so gravity is 9.8. And now that we have our equations set up, it's just a matter of making sure we can solve it. I'll walk through this one, steps on this one, since we do have a square root here, make sure everyone remembers how to get rid of a square root. So first, we divide 6 by 2 pi, and we get 0.955. The right side of the equation remains the same, except we move 2 pi over. Then to get rid of a square root, we're going to square both sides, so we end up with 0.912 equals the length time divided by 9.8. Finally, to solve for L, we have to take that 0.912 and times it by gravity 9.8, and we end up with 8.94 meters in this case. So hopefully these couple examples help you as you work through your assignment. If you do have any questions, any concerns, please let me know, and we'll try to help you best we can. Otherwise, good luck.